Okay, so for chapter 1, I have what I call our 3 goals. Number 1 is valence electrons and the types of bonds. Number 2 is Lewis dot structures and how to use them. And we're going to use those Lewis dot structures to show us the difference between certain functional groups. And the 3rd goal is hybridization molecular shape. Hybridization is a key thing in organic chemistry. And so what I'm going to do is every time we have a functional group or a carbon, I'm going to say, what's the hybridization? Okay, and I want you to be able to kind of think, oh, it's this, it's always this because, or it's this because, or it's this because. Okay, so I want you to start seeing this kind of repetitive pattern and saying that, oh, okay, wait, I don't know a lot about this compound, but hey, it's this shape, which means it's going to do something like this. You'll start to see trends within the system, thinking about the electrons, thinking about the where the electrons are with the Lewis dot structure, and what the hybridization is on the individual atoms we're talking about. So all 3 of these keys tie into the subtle subtext of every different reaction we do from now on, okay? So when we talk about the atom, like I said before, the nucleus all it does is tell us which element we have, okay? The number of protons says which element it is. The number of neutrons gives it mass and tells us which isotope it is. But all the bonding takes place with the electrons, okay? And the fact that electrons have a negative charge is very important. And the fact that electrons, those negative charges repel each other is also very important, okay? So, taking that into consideration now, because the electrons tend to repel each other, there has to be something that keeps them in place, okay? And we call those energy shells, okay? So a shell is basically that kind of imaginary place in space where the electron might be, okay? Is it a hard shell? Can you knock on it? No. This electron is moving around near the speed of light, but 99% of the time, it's going to be found in that space, okay? So it's not that the electron looks this way or has this shape. It's just that most of the time, it's found in that region, okay? So we have different shells based on how big the atom is. For example, hydrogen and helium only have 1 electron shell, that number 1 electron shell. Because it only has that 1 electron shell, it can only ever have 2 electrons, okay? Now, when we move to carbon, boron, nitrogen, oxygen, and fluorine, which are the elements we will be using a lot in organic chemistry, we now have a 2nd shell. And in that 2nd shell, we want to put 8 electrons. Remember that number, 8, okay? So most of the time, we are looking to have 8 electrons around those elements that have that 2nd shell. Again, hydrogen and helium will only have 2. Anything that has that 3rd shell of electrons, like sulfur or phosphorus, can have more. So we can have more than 8 electrons, okay? But anything that only has that 2nd shell, and I'll show you where to find that on the periodic table here in a minute, will have that 8 electrons. So those 8 electron number is something we want to look for, okay? Okay, and my iPad is not liking me. Okay, so the other thing is, because everything is about the electrons, okay? Everything is about the electrons, and electrons are kind of like water. When you pour water into a glass, it fills from the bottom up, okay? So if you think about the bottom being the lowest energy because of where, gravity's pulling it down, electrons are going to do the exact same thing. So if you only have 1 electron, it's going to be in that 1s orbital, because that's the lowest energy. And then as you put the 2nd electron in there, it'll fill that orbital. And then if you add another electron, it has to go to the next energy level shell, which in the case of our drawing here is this next level here, this 2s. So our 1st electron is going to go here, our 2nd electron is going to go here, and then the next electron is going to go here, and likewise, okay? So we're always going to fill from that lowest level, okay? So as we start filling this up, we can start adding electrons to these different shells, and depending on how many electrons we have in that number 2 shell, that number 2 energy shell, we might be able to blend those orbitals together to give us hybridization. And it's all about saving energy. And I'll tell you a little bit more about that in our goal 3, okay, our hybridization goal. Okay, but the key here is it's all about the electrons and where to find them. Okay, so like I said before, we fill from the bottom up, and so our lowest shell is our number 1 energy shell, and it only has 1 orbital, and it only has 1 shape. That 1 shape is spherical, okay? And that 1 shell is completely encompassed by the next shell that you build over it, okay? So our number 1 shell is completely inside our number 2s shell, okay? So that being said, we had to fill these first, and now that we filled this orbital up and we have electrons on this orbital, these electrons can't play around, or we can only play around with the electrons on that outer shell, okay? So that means these electrons in the outer shell are the ones that are going to do the bonding, okay? So think about it as those inner shell electrons, they're locked inside, and our outer shell electrons are the ones that can come out and play, okay? So that being said, that's fine for an s orbital, but when we looked at that energy diagram, right, there are 3 dashes for that p, meaning 3 orbitals that are of the same energy, okay? Now, we've labeled it P because those electrons show up in a different place in space. 99% of the time, they show up in this dumbbell-shaped space, okay? So when we go to our system here, if we think about one of those little lines that can hold 2 electrons, and we know it's dumbbell-shaped because it's in a different orbital and we need to fit a total of 6 more electrons in there, the best way to do that is to divide these orbitals into these dumbbell shapes and then put them on 3 different axes, okay? So when we do that, we have 2 electrons can be on the x-axis in a dumbbell shape, 2 more electrons can be on the y-axis in a dumbbell shape, and 2 more electrons can be on the z-axis in a dumbbell shape, okay? So this is our first set of p orbitals in our number 2 energy level, okay? Now, what happens when we have a big enough atom to get to our 3rd energy level, our 3rd shell? That 3s completely encompasses all 3 of those p orbitals, okay? So if we look at the diagram again here, we see that this next level up, right here, this 3s orbital is higher in energy, which also means it's further out from the nucleus and completely encompasses the 1s, the 2s, and the 2p orbitals completely. So once we start generating electrons in that 3s orbital, all those other electrons are inside and therefore can't play. Only the electrons on the outermost shell will bond, okay? That key feature will help you think about how many electrons we need and what is actually doing the bonding is those electrons. Okay, so we have s orbitals that are spherical. We have p orbitals that are dumbbell shaped, and each orbital we want to put 2 electrons in, okay? But I just said that electrons have a negative charge, and electrons want to repel each other, okay? So what keeps them together in that same energy orbital, okay? What keeps them together in that same energy orbital is the fact that they spin. And when you spin something that has an electric field in it, it generates a magnetic field too, okay? In physics, you may have taken physics and you have what's called the right-hand rule. You have your velocity, you have your electronic component, and then your hand creates the magnetic component. So, but even if you don't know that, you know, magnets have a north pole and a south pole, right? And so once you create this magnetic field, the way you can have 2 electrons occupy the same energy level is to have them spin pair, meaning that now the North Pole and the South Pole of the two different electrons are aligned up. So whenever we fill an electron shell, we put one electron in, and we typically put it spin up. And then to get that second electron, we have to spin couple it in the opposite direction. So we always put it down, okay? So that's how we can pair electrons in an orbital, and they can have those two electrons in that same space without repelling each other, okay? So in a 1s, we only have the one orbital, and it's spherical. In the 2s, we only have one orbital, and we can have two electrons in it, and it's spherical. But in the 2p, we have three different equivalent energy orbitals that are dumbbell shaped, one in the X, one in the Y, and one in the Z. Each of those can have two electrons if they're spin coupled, okay? So this feature allows us to understand, number one, why electrons fill from the bottom up, why we can put two electrons in the same orbital because of that spin coupling, and why the electrons on the outer side are the ones we can play with because they completely encompass the inner shells, okay? Sorry about that. Yeah, 5 minutes. All right. All right. Okay. So let's look at this diagram again with everything I just said, okay? So if we only have something that has two electrons, we have two electrons, and they're always going to be in that 1s orbital, okay? As we add more electrons, we will start filling from the lowest energy up. And in organic chemistry, we have a total of 6 protons, which means we'll have 6 electrons. And so we'll fill the bottom S, the 1s first. We'll put 2 electrons here. Then we're going to put an electron here, an electron here. And we have 1 electron here and 1 electron here for a total of 6 electrons in carbon right here, okay? Now, what leads to hybridization is the fact that we have 1 full orbital, 2 half-full p orbitals, 1 empty p orbital. And we have an opportunity to start blending things together to make 4 equivalent orbitals, okay? But we're not going to do that until goal 3. I just want you to see that the energy diagram is telling us why we're going to get that hybridization, okay? Okay, so let's talk about bonding, okay? So from everything I just said, the electrons do all the bonding, okay? And there's a couple different ways that they can do it, okay? Number one, if you can easily give up an electron or easily accept an electron, it's possible to just transfer that electron to the other atom. And when you do that, you now have an imbalance of electrons to protons, right? So let's say we had something like sodium. It has 1 electron in its outer shell. And it's easier for it to just give up that electron and become a positive charge. And then something like fluorine, which only needs 1 more electron to fill its outer shell, to gain an electron and become an anion, have 1 extra electron or be a negatively charged. When that can happen, and that all happens because of electronegativity, it makes a bond called an ionic bond, because now this atom is positive and it's attracted to this atom, which is negative. And that's an ionic bond, okay? These do happen in organic chemistry, although that's not the primary type of bonding we do, okay? In organic chemistry, instead of giving the electron away, I'm going to share my electron with the neighboring atom, and we're going to share these, okay? Doesn't have to be equal. It just has to be shared so that part of the time I get the electron, part of the time you get the electron, and that we still have a balanced charge. And that sharing is what we call that covalent bond, okay? So, and that covalent bond is a total of 2 electrons, because one atom is giving one of the electrons to share. One of the atoms is giving another electron to share to create 2 electrons to create a covalent bond. All covalent bonds are a sharing of 2 electrons, okay? Now, we can have multiple bonds, which means we have multiple shared electrons, but that'll go. Now, within covalent bonds, we can also have two types of bonds, okay? In those two types of bonds, we have what we can call non-polar, meaning that I have electrons, you have electrons, and we both want the same amount, we both tug on the electrons the same amount, which means we can share these evenly, okay? That's a non-polar covalent bond, okay? Now, if I want electrons more than you want electrons, but not so much that I have to steal your electron away, then I'm gonna make a polar covalent bond, meaning more of the electron density stays with me, but I'm still sharing, and I'm still sharing with that to give us that polar effect, okay? Now, if I'm so electronegative, I'm gonna steal your electron away, now I become an ionic bond. So all three of those bonds have everything to do with those electrons that we are trying to share, and if we can't share, we become an ionic bond, okay? Now, this all comes down to electronegativity, okay? All right, so what's electronegativity? Electronegativity is basically an atom's attraction to electrons, okay? So if I am a small atom and I can pull on my electrons with my nucleus really tightly, then I have a very high electronegativity, okay? So that's why fluorine, which is a very small atom with a total of 9 protons in it, and it has it wants to pull on those electrons very tightly, it's the highest electronegative atom, okay? So what it's doing is it's saying, okay, I want electrons more than anybody else. I'm selfish fluorine, and so I'm going to pull on electrons more than anybody else. However, this trend kind of decreases as you move away from fluorine. So fluorine is at that top side here. As you go up and as you go over right here, fluorine's the most electronegative here. And then it decreases as you go down from there, okay? So the key here is to think, how far apart are those atoms on the periodic table, okay? So let's look at our periodic table, and this is color-coded to show you kind of the electronegativity values here, with fluorine being the highest right here, and I'm gonna do it in green, so it'll be different right here. Fluorine's the highest right here at 4. It's an arbitrary number, but it's just, they're measured values, okay? So all these small materials right here have the highest electronegativity values, meaning they're the most likely to pull electrons toward it. So if you're close, let's say in this blue region here, right here, these are going to just make polar covalent bonds because they're tugging on it, but they're still close in electronegativity that they can make a shared bond and still pull on it, but not pull the electron completely away. As we move out to this red zone here, right here, as we move so far away from there and the difference between electronegativities is so high, now we're getting to the point where those things are going to give up their electrons. These are going to give away an electron to our fluorine so that it'll make an ionic bond. So what we're looking for is that Goldilocks band of things that are close enough in electronegativity that will share those electrons with these materials without taking them away. And that's where we get polar covalent bonds or non-polar covalent bonds, okay? So there's an actual value associated with this. So if the difference in electronegativity is less than 0.5, we have a non-polar bond. They both wanted about the same amount, so they're tugging maybe a little bit, but overall that bond is equal on both sides, okay? So what does that tell us? If that bond is kind of equal, those bonds tend to be less reactive because there's nothing pulling the electron one way or the other to make it reactive on either side. So bonds like a carbon-carbon bond, single bond by itself, are not very reactive because they have a non-polar covalent bond. Carbon-hydrogen is only 0.4 different. They have a non-polar covalent bond, so it's not a very reactive bond. But then once we go to slightly higher, 0.5 to 1.9, now that's a polar covalent bond. So like chlorine and carbon are different by about 1.2. And so now, because that bond is polar covalent, we're going to start to do chemistry on that bond. That bond is going to be reactive. We can displace that. We can substitute it. We can remove it. We can do chemistry. So that's what the concept of that polar covalent has to do with organic chemistry. The more polar the covalent bond, the more reactive that bond is. Okay, so when we think about these and look at their differences here, and you're kind of confused, well, why is that bond so reactive? Think back to, ooh, it's a polar covalent bond, or it's a really polar, it's almost ionic. So that's why those are more reactive than other things. You can tie them all to how polar that bond is. Okay, all right, let's go here. All right, any questions on that right now? Unmute, chime in, or put it in the chat. I'm going to go into a little more detail about why something might give away electrons and might accept electrons here. If we have no questions. Okay, okay. I'll keep an eye on the Zoom here, on the chat here. So part of that has to do with our electronic configuration, okay? In Gen Chem, we saw that orbitals like to be empty, half full, or completely full. Okay, because when the electrons are spin coupled and spin paired, or they don't have to be spin paired, that's why a full orbital or a half full orbital makes sense, because there's a little bit of energy associated with that spin pairing or having an empty orbital. So when we can fill an orbital or have an orbital completely empty, there's an energy savings there, okay? Now, the thing that'll drive that when we form ions is that difference in electronegativity. Instead of trying to share those electrons that are on those outer shells and make a covalent bond, it takes less energy because one of them wants the electron more to just say, okay, fine. In this case, we have sodium right here, has one electron in its outermost shell, okay? So it's the electron that's going to do all the work. It's going to bond. It's either going to form a covalent bond or form an ion. Okay, and then we have fluorine right here, and fluorine has 5 of the 6 electrons it wants in those 3 equivalent p orbitals. Okay, so it's only missing 1 electron, and it's really electronegative. So it wants the electron more than the sodium does. So it makes sense for this electron to be transferred from the sodium's outermost shell. It's only half full. Give it away. So now sodium has a complete full shell, but a positive charge, okay? It still has the same number of protons, and we gave away 1 electron, and so now it has a positive charge, and we get to that point, okay? So, but the fluorine here, it had a half full, it had 1 electron missing out of an orbital here, and it is more electronegative. It likes the electrons, and so it pulls it away, and it now has a full outer shell, and because it has 1 more electron than protons, it is negative, okay? So having that half full, completely full, or empty shell is a driving force. The second driving force in ionic bonds is electronegativity, okay? When we go to covalent bonds, we're looking to do a similar thing where we want to fill the outer shell. We want it completely full or completely empty, okay? But we don't have enough electronegativity, to pull the electron away from the other compound, from the other atom. So because we can't pull it away and make it ours completely, we're gonna share, okay? So if we look at hydrogen here, we have 1 electron in that s orbital, and we have 1 electron in this s orbital here. And an s orbital wants 2 electrons, okay? So instead of because these both have the same electronegativity, there's no reason for it to steal it. So it's like, well, okay, I'll have it half the time and you have it half the time. We'll share it evenly, we'll share it equally. And guess what? 90% of the time, my outer shell is completely full. 90% of the time, your outer shell is completely full. So that sharing works to fill our orbitals, okay? When that sharing works to fill our orbitals, we're making that nice bond, we're making a covalent bond. In this case, because the electronegativity of the two hydrogens are both the same at 2.1, that means that bond, those electrons are evenly shared, and so we have a non-polar covalent bond because we're sharing those electrons to fill our orbitals at least part of the time, okay? Does that make sense? I mean, we're filling our orbitals by sharing electrons at least part of the time, okay? That's our driving force for making these bonds, okay? I think it's really, really important. Okay, so again, if the electronegativity is not too different, not greater than 1.9 on the scale difference between the two, we'll still share those electrons, but not equally, okay? So we're gonna see this representation in these polar covalent bonds time and time again. And what we're gonna have is a symbol here that when we have a negative charge, a partial negative charge, meaning more of the electrons are being pulled toward the chlorine than the hydrogen. So that makes a slight positive charge on the end here. And so the electrons are being pulled in this direction here, okay? So it's not a full negative charge. It's a part negative charge. So it's a partial negative charge. Whenever we see a partial negative charge and a partial positive charge on the bond, that's where the reactivity is going to happen. That's where you need to say, oh, wait, hold it. Well, I have a polar bond here. I bet that's going to play a role somehow in this reaction, okay? And likewise, the side that has the less electron density or is less nucleophilic will have less of that electron. Oh, come on. Gotta share again. My iPad decided to stop sharing. Let me reshare. Or my internet went down. I don't know. Uh-oh. Oh, that's why. It's hooked up to the wrong internet. That's why. Everybody hang on for a second. Technology is great until it's not. Okay, let's see. Talk amongst yourselves. Let's see. There we go. There we go. I'm back. All right. So yes, on Canvas and PowerPoint, I will have the full slides, the full set of slides for all of the video lectures. And then I'll have the additional slides, what I call the goal slides, also posted separately, okay? And then these videos will also be posted separately. So to answer the question on the chat there. Okay, getting back to where we were. If the less electronic...
I am.
You're on mute.
I am.
Jenna?
I remember y'all too.
Dr.
I
Irvin, you're on,
remember y'all too.
you're on
Wait.
mute.
Oh,
You're on mute. There you go.
All right, I'm back. All right, sorry about that. All right, there we go. So yes, all these slides will be posted. That's the last thing I saw in chat. And it looks like we're still recording. So let me get back to sharing with our slides here. See if I can. There we go. Technology is great until it's not. Okay. Okay, so I hope the last thing you heard was something about a polar covalent bond being partially positive on one side and partially negative on the other. Did we get that far? No? All right. What's the last thing we heard? Anybody? Anybody? Am I still on mute? Okay, well, I'm gonna redo this slide then, and so we can get to there. Everybody can see the slide, right? It should say polar covalent bonds at the top. Yeah, okay, everybody got a thumbs up there? Okay, great, all right. So this is a feature that's kind of important in, especially if you're starting with a new functional group or a new compound you really haven't seen before. This kind of identifying whether it's a polar covalent bond and where the polarity lies will help you identify how the reaction might work, okay? So in this case here, the more electronegative atom is gonna pull more of the electron density toward it, okay? So it's not gonna steal the electron, it's just gonna pull it there more of the time. And so because of that, there's gonna be more of a negative charge on that atom. It's not a full ion, it's just more electron density is pulled to that side. And in contrast, that means the one that's less electronegative has its electron density being pulled away from it and is partially positive, okay? So when we look at a new functional group, we want to identify, oh, is it a polar bond? If it's a polar bond, then I'm going to have a partially positive side and a partially negative side. And that partially positive side is going to react with things that might be negative. And that partially negative side are going to react to those things that are positive. So just looking at the polarity of a bond might give us an idea of what might happen next, okay? That's why, you know, kind of this is a fundamental goal in understanding that these bonds can be polar and it leads to their reactivity. So you'll start seeing this time and time again. Every time we introduce a functional group, I'm gonna say, what's partially positive, what's partially negative, what's the hybridization? Because these are gonna be keys in moving through organic chemistry without having to remember everything, okay? So the summary for goal one, and goal one is valence electrons, which are the outer shell electrons, are the things that control what kind of bonds we have. And the three kinds of bonds we have are the ionic bond, the covalent bond that's polar, and the covalent bond that's nonpolar, okay? So those are gonna control our types of bonds we have, okay? We always fill from the bottom up, okay? The two orbital shapes we really need to play with in organic chemistry are the S, which is spherical, and the P is dumbbell shaped, and that the electrons do all the bonding. Not only electrons, the outer shell electrons do all the bonding. If we can keep track of the outer shell electrons, we can keep track of the bonding. If we know the electronegativity, we know the bond type, okay? So that is chapter one, goal one. Anybody have any questions on this before I move on to chapter one, goal two? Okay. All right, so I'm probably gonna be about halfway through chapter one, goal two before our time runs out. I'm gonna try to end on time, even though we had a technical difficulty. I will pick it up there tomorrow and we should get all the way caught up. So again, homework isn't due till Friday, so don't worry about that. Try to go back and view some of the videos for the longer sections and then look back at these and say, figure out why I think these are the most important goals. Okay, just kind of giving that secondary iteration, Okay. All right, I'm going to start this real quick. Okay. Okay. So our second goal is all about Lewis dot structures. Okay. This ties into that idea of valence electrons because when we look at the Lewis dot structures are going to, number one, tell us several things. How the bonds are structured, like what the kind of, it'll help us decide what the shape the molecule is. It'll help us to see where the electrons are. Knowing the different atoms will also tell us whether it's a polar or a nonpolar bond. So Lewis dot structures and mastering Lewis dot structures tells us a lot about keeping track of how many electrons we have, where the electrons are, and what kind of bonds they make, okay? So again, the valence shell is the outermost electrons we can play with. Remember, they completely encompass all the lower energy shells, so only that outer shell is the most important electrons to play with. These are the ones that form the bonds, okay? And by keeping track of just those outer electrons, lets us keep track of where the bonds are and what types of bonds we have. Okay. So we can either memorize the idea of, oh, well, hydrogen always has 1 valence electron, carbon has 4 valence electrons, and oxygen has 6 valence electrons. Well, yeah, we're not in med school. We don't need to memorize things. We are going to figure this out by looking at the periodic table. Okay. So the periodic table has gobs and gobs of information on it. And so you need to have that map of how to use it, okay? So the great thing about this periodic table is that it tells you how many valence electrons there are. Not only that, we also can use the periodic table to figure out, well, is one more electronegative than the other, right? So if we look at this A number here, so without the A on it, they number from 1 to 18, okay? And so that tells us something, and that's okay. But if we look at the A number, it tells us how many valence electrons there are in that element, okay? So this A number attaches to this column, which means every single atom in that column as a neutral atom has 1 valence electron, okay? So if we go down to rubidium, we have 1 valence electron in its 5th S shell, okay? We know that because all of these are S orbitals, and all of these are P orbitals. And then if we get into organometallics, we can go to the D orbitals, and then these are the F orbitals way down here. So all of these are S orbitals, and so there's 2 electrons available in an S orbital. So if this is our 1s orbital, that means the next element over is our 1s orbital, but it'll have 2 electrons in it. Now, turns out helium really should be over here on the periodic table because it only has 2 electrons. So it should really be in that box. And sometimes you actually see it in that box because it tells you it has 2 valence electrons. Okay, so if we move down to the next row here, we start our 2s. So we have our 2s's, lithium and beryllium. But look here, we have carbon right here. Carbon means it has electrons in its p orbital because that's where p's are. They're over here, okay? But it's in a 4a group, okay? Okay, just knowing it's in that 4a group knows that we have 4 valence electrons, okay? And if you forget or stress out or get, a panic attack, all you have to do is look at the table and say, oh, there's that many valence electrons. So that means fluorine has 7 valence electrons, oxygen has 6 valence electrons, boron has 3 valence electrons. Boom. You don't have to memorize anything. You just need to look at your periodic table. Okay. Does that make sense? Okay. All right. Go ahead, and this is our time is 1:40 right here. I'm going to try to start on time and end on time because your time is valuable. So I will continue with chapter 1, goal 2 next time, tomorrow. And then we should get all the way through chapter 2, goal 3. So be prepared on all of chapter 1 and all of chapter 2. Again, I will release the rest of the videos tonight, tomorrow morning, and we should be all caught up by Wednesday, okay? If you haven't signed into Top Hat and you want to continue on the course, please sign on by Wednesday. We have a mock test Wednesday afternoon, okay? Questions before we leave? All right, if you want to go ahead and leave, go ahead and leave. If you want to stay behind and ask questions, you can, all right? So see you tomorrow. Stop sharing. Sorry about my cough.
Thank you, Dr. Irving.
Well, thank you. See you tomorrow. If you don't have questions, if you have questions, stay on. Let me stop recording since the class is over.